Hey, it's Mr. Shrum, and I am going to go through these tutorials with you and add a little bit of commentary or tell you where to pay attention to the most. But this one's all about math and systems of measurement and why it matters in the realm of physical science and how to go about these mathematical operations. But first, we talk about the system of units. So first we have Kelly. She's traveling in France. She notices everything's not like she's used to in the United States. Miles are not being used. Pounds and ounces are not being used. Gallons. Everything's listed in this other system. And this system is known as the International System of Units. We'll get into this in the next slides. Bam. So in France, it's known as the SI system from its French name. So anytime you hear grams, kilograms, meters, kilometers, liters, milliliters, that is the SI system. So the US has adopted it and they use it in global trade because if everyone else is using this one system, you have to kind of learn the language. The same way countries learn English because lots of other countries and lots of other people learn English as a second language. So if everyone speaks at least a little English, it's a little easier to communicate. Same thing with the system of measurement. If everyone uses the SI system, it just makes things easier to communicate. So here we have the quantities listed, the units listed, and the system symbol for each one. And prefixes, you notice that before each like base, so we have, these are the base units. Right. And depending on the prefix that comes before this word, that tells you how large or small the unit is based on this first unit, okay? So for instance, kilogram is made up of kilo and gram. Kilo is thousand, okay? Think of that as 1,000. So that literally means 1,000 gram, okay? Kilogram. So that's 1,000 grams. So it makes sense. Kilometer is 1,000 meters. Centi means 100th. So like 1 divided by 100 is 100th. So a centimeter is 100th of a meter. So another way to look at that is 100 centimeters equals 1 meter. Okay? And same thing with liter. The prefix milli means 1,000th. So 1 divided by 1,000. And that means 1,000 millimeters is equal to 1 meter, okay? So kilometer is the base unit. Or, sorry, the meter is the base unit, and then anything you attach to the front of the word, that tells you more about the unit of measurement. And if this helps you visually see what I'm talking about. So we talked about kilo. 10 to the 3, 1,000, 10 to the third power, sorry, centimeter, 10 to the negative second power, which is the same as 1 divided by 100, 0.01 milli, 10 to the negative third power, which is the same as 1 divided by 1,000, so that's 0.001, okay? And they can get really small or very large, okay? And here are some examples of the way the math works out. So you're using the ratios, okay? Example 1, 100 meters, how many kilometers is that? If you know the ratio is 1 kilometer to every 1,000 meters, you can multiply 100 meters times 1 kilometer divided by 1,000 meters. These units cancel out, meters with meters, and you're left with kilometers, 0.1 kilometers, okay? Think of these as ratios. The second example, 1.2 kilograms. How many milligrams is that? So we remember that 1 kilogram equals 1,000 grams, and 1 gram equals 1,000 milligrams. So you take 1,000 times 1,000, and that is 1 million milligrams. So you take 1.2 kilograms, multiply that by the ratio, 1 million milligrams divided by 1 kilogram, okay? Kilogram cancels out with this kilogram, and you're left with 1,200,000 milligrams, okay? So get that pattern down. So where you take a number, multiply it by a ratio, this unit cancels out with this unit, and you're left with the unit you're trying to convert to. Yeah. Okay. Scientific notation is a way to write out large or small numbers in a more simplified way. So if something has lots of zeros and you don't want to write out like 10 zeros or so, you can use this scientific notation. And really it's made up of 3 parts. The coefficient, which is the first 2 digits usually, first 2 digits, multiplied by a base of 10 to the exponent power. So in this example, you have 4.5 times 10 to the 9th. And this number tells you how many times you move to the right, okay? 4.5, move 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay? So that's how many zeros you fill in afterwards. So you have 1, 2, 3, 4, 5, 6, 7, 8, 9 numbers all together following the 4. Okay? This decimal place moves to the right 9 times because that is the power here. All right? We'll look at some examples. And if it's a large number, this exponent is positive. But if it's a really small number, as in it's 0.0000, that base turns negative because that means you're moving this decimal place to the left and not the right, like it would go up here. All right? Positive numbers move the decimal place to the right. Negative numbers move the decimal place to the left. Okay? Pay attention to this base number. And this gives you examples. So 1,200,000. So how many numbers are after this first digit? 6 numbers altogether. This decimal moves 6 times. So we have 1.2 times 10 to the 6th milligrams. Okay? Let's try this one. So 0.000000061 kilometers. So how many numbers are before this decimal place? So we have the 6, we have the 6, and then 3, 6, 7, 8 zeros before it. So that would be 6.1 times 10 to the negative 9. So there are 9 digits. The decimal moved 9 times to the left, okay? You'll get this with more practice. And this goes through converting scientific notation to standard notation. And all this means is the decimal place is moving. Positive to the right, negative to the left. So this is an activity where you convert and use scientific notation. Practice that. See how well you do with that. And then this has the steps and outcomes of what to do. I think we'll step past that for now. So let's practice this one. This one seems quick enough. 1, 2, 3, 4, 5, 6, 7, 8, 9. Wait. Yeah, 3, 6, 9 zeros, 2, 3. So if it would be 2.3, see how these all have, well, it should be 2.3. And then since the decimal place would be between the 2 and the 3, it moves over 1, 2, 3, 4, 5, 6, 7, 7, 8, 9, 10 times. So if we're moving to the left, that means the power has to be negative, right? So 2.3, the second one's wrong, the last one's wrong. So it's either A or C. And since it's moving to the left, it's that first one, okay? Negative power to the left, positive power, decimal place moves to the right, okay? Yeah, that's wrong. Or well, they're just describing it in the opposite way. Yeah, okay. So I guess it depends from which way you're talking about at first. So if you're converting one way to the other, then you're saying the decimal place moves a certain way. Yeah, okay. Never mind. It was fine. It depends on the perspective. Now we're talking about qualities of a measurement. So if you hear words like accurate and precise, that means something very specific here. And it gives you a few ways to think about it. So A, pretend this is a dartboard or a gun target, I guess. If all of your shots land here, that means you're very accurate, okay? You're trying to shoot this and your shots are pretty close. Now, if you land all of your shots really close together, but nowhere near the target, that is how we refer to precise. So your shots are close together, like very close together, even more so than these ones. But you just weren't accurate. Okay. So this is accurate, not precise. This is precise, not accurate. C is both precise and accurate. So you hit the target, and also all of your shots are placed really close together. So precise means the results are reproducible. So like you're getting the same or very close to the same thing every time. If all of your darts land near the bullseye and near each other, they're accurate and precise. It's accurate and you're reproducing very similar results. But if you're neither accurate nor precise, you're missing the target and you're like nowhere near close to the other ones. Okay, this is the best place to be because you want to be right, and you want to be right every time. Okay, this is like you're right, but you're not always right in the same way. And this is like you're getting the same thing every time, but you're not right. Okay. So we want to have the correct measurement, and we want to get the correct measurement every time we're using a tool. And a lot of times you need to balance this out. Sometimes you can't always have both as much as possible. Sometimes things are too expensive to have super accurate and super precise measurements, but that's a story for another time. But yeah, precise measurements. If someone else does the experiment and gets the same measurements, then it's precise, reproducible. So they're given a pipe 1.32 centimeters. They measured it 5 times. So you notice they're pretty close together, but they're not close to the actual value. So I think that looks most like this one. So their target is 1.32, yet they keep getting like 1.48, 1.49, 1.52, and that's not close enough to this. So I think these are precise because they're pretty close together. However, they're not accurate. So they're just precise. Significant figures. This throws off a lot of people sometimes. When you use a ruler, a balance or scale for mass, thermometer for temperature, every time you read a value, there is some amount of uncertainty associated with it. The accuracy depends on the precision of the tool you're using to measure. So I think the easiest way to think about it is the balance. Two objects were weighed with the same tool to the third decimal place. So you can measure 0.001 gram of something. So 12.234 grams for object A and 0.030 grams for object B. That final zero, that tells you something important, that the tool itself can measure up to the third decimal place. Okay? So if it was just 0.03, that means that the tool cannot measure up to the third decimal place. Yeah. So the more accurate it is, the less percentage of error you can find in an object measurement. And significant figures is this special use of the last digit. All non-zero digits, 1, 2, 3, 4, 5, 6, 7, 8, 9, are significant. The value 23 meters has two significant digits. So wham, bam, 2, because they're all non-zero. All zeros between two non-zero digits, sandwich zeros, are significant. So 1, 2, 3, 3 significant figures. Okay, so 2 sig figs, 203 sig figs. Sig figs is like the shorthand nicknamey thing you can use for significant figures. Zeros that are both to the right of the decimal point and at the end of the measurement are significant. So that, significant, right? That's different than this, 23. Okay? 23.0 means that you can get more accurate than this. You can verify up to the first decimal place, while in this one you can't. So that 0 is significant. That's why these are called significant figures. They have meaning, and they tell you about the tool. If a decimal place is displayed in a number greater than or equal to 10, any zeros to the left of the decimal point are significant. So same thing up here. 20.3, significant, because this digit matters. Therefore, the ones in between also matter. Okay? Sandwich. It's still sandwiched like this one before. So this has 3 sig figs. 3 sig figs, 3 sig figs, 3 sig figs, 2 sig figs. Zeros that are merely used as placeholders are not significant. For example, 0.0023, they're not sandwiched between any other number, right? They just have a 0 to the left, decimal point, 0023. So these are the only things you really can pay attention to. 2 and 3 are significant. These other zeros are not. So, considering this, how many significant figures is it? We have 1, 2 on the left-hand side of the decimal point, and then 3 on the right-hand side. So that is 5 altogether. However, this one has 2, okay? So 0.0, nothing sandwiched between these. So just the 3, and then the last 0, because that ties back to this one. No, this one. The 0 at the end of the measurement means that you can be accurate up to the 3rd decimal point. So 2 significant figures here. And when you add and subtract sig figs, there are certain rules. If you subtract something with 2 different significant figures, you use the most accurate. Or the least accurate, sorry. When you add, you have to use the least accurate number because that's the limiting factor here. So 25.113 plus 3.5. This one only has 2 significant figures. So here we can only use we can only be as accurate as one number after the decimal point, okay? So we have 28.613. However, this one's not accurate enough to use these 2, the last 2 digits. So we have to only use 28.6, okay? If you're adding, go to the number with the least significant figures, and you can only be as accurate up to this point, 0.5. So 0.6, 28.6 is as accurate as we can get. Now, if you're multiplying or dividing, you can only be as accurate. You can only contain as many significant figures as the least accurate number you're multiplying or dividing by. So you're counting significant figures instead of decimal places, like in the last one. So if you're subtracting or adding, you're paying attention to decimal points. If you're multiplying and dividing, you're paying attention to the significant figures. So if you're multiplying 2.345, and that has 4 significant figures, by 5.45, which has 3 significant figures, you can only have an answer with 3 significant figures. So it would be 12.8. Okay. Here's another example. 45.35 by 9.5. 4 sig figs multiplied by something with 2 sig figs. You can only have 2 significant figures. So you would round up to 4.8. Okay? Remember this. This will be easier when you practice. And here you get lots of practice. So here, you can only be accurate to this decimal place because that's the least accurate. And you're adding. But now we're multiplying in this one, and the answer can only have 3 significant figures. So remember that. You're subtracting, you can only be accurate up to this decimal point. You're dividing, so you can only be accurate to 3 significant figures. Okay? Okay. So, this asks the key difference between adding, subtracting rules versus the multiplication and division rules. And which one sounds like the most correct? It's this one. Okay. So remember, adding and subtracting, you have to round off to the same number of decimal places as the value with the fewest decimal places. But when you're multiplying and dividing, you must round off to the same number of significant figures as are the value with the fewest significant figures, okay? Yeah, more practice and you'll get it. Scalar and vector. Scalar are just measuring magnitudes. However, vectors contain a direction. If you have magnitude and direction, that is a vector. Scalar is just magnitude. It does not give you a direction. And we'll look at some of this. Speed and velocity. Speed is scalar. It just says how fast you're going. So 12 kilometers per hour. It doesn't tell you which way. But velocity, it can tell you both magnitude, 12 kilometers per hour, and direction, north. So there's more information in a vector quantity. Average speed versus average velocity is just dividing distance travel in total divided by the time, the total time of travel. So if you covered 10 kilometers in 1 hour, your average speed is 10 kilometers per hour. However, the average velocity is equal to the displacement, or change in position, divided by the total time taken. So velocity equals displacement divided by time. So here, the displacement from the start and end is 1.2 kilometers. You start here, but you're in around this way. However, from the starting point, you're 1.2 kilometers away. So we have 1.2 for displacement divided by the time, is 1 hour. So if you took an hour run to run this kilometer path, 10-kilometer path, your average speed would be 10 kilometers divided by 1 hour. However, the velocity, the average velocity would be 1.2 kilometers divided by 1, or 1.2 kilometers per hour, at a heading of about 110 degrees, according to the compass, okay? In figure B, the starting and ending point are the same, so the displacement is 0. If you took an hour to run 10-kilometer path, your average speed would be 10 kilometers per hour, but your average velocity would be 0 because you're at the same point you started. You weren't displaced, right? You didn't, the direction. So speed changed, magnitude of speed, but you didn't change direction. So the vector quantity of velocity is 0 because there was no change in direction from the start and end point. So we have an example. Bill, started from his home and cycled 6 kilometers west to meet his friend. He rode another 8 kilometers south to a bookstore. After buying books, he rode 3 kilometers east to a florist, and then rode another 4 kilometers due north. He took exactly 3 hours to get from home to the park. So the average speed would be adding up everything, the total distance he traveled divided by the total time. So 6 plus 8 is 14, plus 3 is 17, plus 4 is 21, divided by 3 hours in total. 21 divided by 3 is 7. Okay. However, how much was he displaced from the starting point? So if he went 6 west, another 8 south, 3 kilometers east, and then 4 kilometers north. Five divided by 3. Okay. So, all in all, he is 5 kilometers away from his starting point after all this business, because he went west, south, but then he went back up north and back east. And that leaves him 3 kilometers west from his starting point and 4 kilometers south. So forming a triangle, he is 5 kilometers away if you use geometry to find that. 5 kilometers divided by the total time, displacement of 5 kilometers divided by 3 hours, he is 1.67 kilometers per hour southwest west, because the direction is included. And here's the summary. And hopefully we go over more stuff and you'll get a better feel for how all of these factor in with physical science. But the important part is we have a system of units. With prefixes, we can refer to how little or how large we are talking about the units and how many units we're talking about. And then we have a certain way to write out numbers. Scientific notation lets us write out large or small numbers with only a few numbers. It's kind of like shorthand, nicknames. 1.2 times 10 to the 6 is 1,200,000. And to get reliable results in experiments, these values have to be both accurate and precise, right? Accurate is very close to the correct value, known value, where precise measurements are consistent and you get the same thing again and again. Significant figures tells us how precise something is when we measure it. When you add or subtract values, you have to pay attention to the number of decimal places the value with the fewest decimal places has, and only use that many decimal places. But when you're multiplying and dividing, you must have the same number of significant figures as the value with the fewest significant figures. And the best way to learn about that is just practice and practice. And lastly, quantities are classified as scalar and vector. Scalar describes magnitude. Length, speed, mass, temperature are scalar because they don't tell you the direction. And you don't need the direction for any of that. But if there's magnitude plus a direction, that's a vector. Displacement, velocity, acceleration, and force are examples of that. Magnitude only scalar, vector, magnitude, and direction. All right. That is our first tutorial. I hope I helped you understand the mathiness that physical science uses. And we will practice this more. All right. I will see you guys next time. Have a good week.